Hello everyone, my name is George Cardozo and today's lecture is going to be about multitask learning and auxiliary tasks. So far, you've heard quite a few things about deep learning, how it works, some of the foundations and the mathematics behind it. You've also seen that there are several frameworks, in this case we've chosen to work with PyTorch, that you can use to make the use of deep learning very simple, plugging in layers together, being able to calculate gradients and being able to backpropagate through those gradients so that you can optimize your network. You've also looked into how do you apply these networks to, for example, many medical imaging tasks, and what is particular about medical imaging data that makes deep learning a little bit more complicated than in some classic computer vision applications. But one other thing that you've seen already is the use of loss functions. And loss functions are the objective that we're optimizing for. Really, the objective of these loss functions is to tell our network, this is what I want you to minimize. And these networks, even though we call them artificial intelligence, they're actually just very smart. Sometimes they can hack their way in order to be able to minimize that loss function. They really try to find many different ways to optimize themselves to be able to optimize for that without actually necessarily solving the problem that we want them to solve. One way to control for this is to actually add more losses to our network. So rather than optimizing for one thing and one thing only, we're optimizing for several targets at the same time. And in order to optimize for several targets at the same time, you will then need to find features and representations that are actually useful for the two things you're trying to do at the same time. And because of this, the network often has less capacity to overfit certain tasks or to give you features that are not really the ones that you might want. This is really the concept that exists in multitask learning, and this is the concept that we're going to explore here today. So by the end of this lecture, we hope to give you some insights about how multitask learning works, what auxiliary tasks are and how can they help the problem. When you have multiple tasks or you have multiple loss functions, how do you stagger them and prioritize them? How do you weight them? And how can you use other things beyond the loss itself? For example, you can use the gradient of the loss to be able to guide that process. Interestingly enough, many of the tasks that we're trying to solve for can be very similar from the point of view of the network. If you're trying to, for example, let's say classify a brain into multiple disease types, being able to classify the disease of the patient might be analogous or might use the same features or might use the same parts of the brain as if you're trying to do another task, for example, being able to predict the age of the patient. And because of this, networks can use this complementarity between objectives to be able to extract features that are more robust. And really at the fundamental level, what we want is for a network to perform well on a series of tasks, not only on the first and on the secondary task, but both of them at the same time. In certain situations, you might also want to use a secondary task purely to help the network on the first task, but you're not actually interested about the second task itself. And that's a really interesting setting, is using information that you have available to you to regularize the network, but the regularization, rather than being prescribed, is by introducing this extra learning process, this extra variable that we're optimizing for. And by doing this, the network has to learn something that is more robust and something that is more generalizable. There's also a really interesting symbiotic relationship between multiple tasks where you're trying to train two things at the same time. And by doing this, the two tasks force the gradients of the network to go in a direction that is useful for both. And by doing this, you can actually have several advantages from the point of view of optimization, where networks might not get stuck in local minima as much as they could before, because now they have a more robust gradient and a gradient that is following a direction that is useful for two things at the same time. So are multitask networks actually useful from a training point of view? The answer in general is yes. Yes, there are situations where it's not useful, and we're going to see later on that you can mitigate most of those concerns. But in most situations, multitask can and will be helpful for your problem. For example, first of all, because we're dealing with biological systems, the features that are learned from data tend to be related to certain parts of the human body, certain appearances or certain locations. And because of those things tend to be biologically informed, they tend to be useful for many different biological processes, including the one you might want to predict as your primary task, let's say diagnosis, but also useful for a secondary task, like, for example, predicting the age of a patient. And it might be that the secondary task can be very strange or often even not very useful, but as long as they share commonalities from the point of view of the features that enable you to predict that end property, then they can still be useful. If you're learning multiple tasks at the same time, the other thing that happens is because the network has a limited amount of capacity, the number of parameters that the network has, it needs to form a more compact and more consolidated representation of the data. Compact representations tend to give rise to more generalizable networks. But there's a balance to be had here. So if you have a network that is too compact, you don't have the expressivity, the capacity to learn a mapping from input to output. But if it is too broad and you have too many parameters, you will need a huge amount of data to be able to achieve the degree of generalizability that you would want. If you train for multiple tasks at the same time, you're naturally forcing the network to fit more information into the same amount of parameters. And because this amount of parameters are fixed, what you can then do is basically what happens in the background is that the network tries to find common properties between them so you can reuse them for both predictions at the same time. So a network will have to share its parameters across the two tasks, which means that the parameters that we'll find will be common, and common parameters are more likely, again, to be biologically informed and then to make predictions that are generalizable. The last thing that it does is because it forces all of these features to be more biologically meaningful, it also ends up generating more robust representations of the data and of the features themselves. So the features themselves become more robust, become less prone to certain types of variations, and that obviously gives rise to better generalizability. Something that is really interesting from the point of view of deep learning applied to medical data is that one of the things that you normally want to do is some degree of data augmentation. This is situations where you're perturbing the input with certain types of degradations or certain types of transformations like geometrical transformations, rotations, flips, or adding noise or changing lighting conditions and things like this. And the reason that you want to apply these is so that the model, first of all, has more data, but also so that the model learns some degree of invariances to those perturbations. So if it sees, let's say, an image, and it knows that the diagnosis of this image is X, if you're perturbing the input by adding different realizations of noise, and the network knows that it needs to always give the same output, the same diagnosis, it needs to learn features that ignore the noise and are still being able to make the same prediction. The interesting thing is, multitask learning can actually be seen from an intuitive point of view, obviously, to be doing the same thing. So by adding multiple tasks, it introduces something that forces the network, again, to have a more compressed representation. And this compressed representation means that features are going to be more biologically informative. And because they're more biologically informative, they tend to ignore things that are spurious or might be related to other random effects like noise. That basically results in better generalization. So even though sometimes you might not see, for example, improved performance on your training set, you often can see that on your test set when applying multitask learning type models. And because different tasks have different noise properties, if those noise properties are not correlated between the two tasks, or if the noise properties of the input are not correlated from the point of view of being able to make that prediction of the output, then the network will learn something that is invariant to those by using the orthogonality between these noise patterns to be able to find what is the true underlying signal and transforming that into a feature that is useful for the network itself. So just to precise this a little bit more, if you imagine that you have a task and the task is, for example, very noisy, or you don't have a lot of data, or the data itself is very high dimensional, for example, 3-dimensional, 4-dimensional, even 5-dimensional data that you might have from the point of view of medical images. If you are in that kind of regime, it can actually be very difficult for a network to be able to have enough data that will teach the network to separate signal from noise. So the network is learning the different convolutional kernels and the different transformation matrices that happen internally. And by doing this, is learning what is the part of the signal that is observing from the input data, and how does it represent those as a series of features, right? And this transformation from an input to a feature space is something that needs to be informed by the amount of data that we have. But if the data is very noisy, or we don't have enough of it, and the number of parameters is large, for example, if you're looking into, 4-dimensional data with three-dimensional volumetric data plus multiple modalities of the same data, you might be in a situation where your convolutional kernels are really big, and that means you would need a huge amount of data to train a network appropriately. So if you don't have that amount of data, the network cannot separate the noise and the signal, and because of this, it will tend to overfit to the data that you give it. And because it overfits to that data, it loses the generalizability. The same thing again applies to multitask learning. If your data is very noisy and you have limited amount of data, using different tasks that have different targets, but that rely on common features, which is I think something that is quite important to say from the beginning. Using a task which is absolutely guaranteed to be completely unrelated will very likely result in a degradation of results rather than improving results. But if you choose a task that might have some analogous and complementary and similar properties to use from the point of view of the image, and will take those properties and transform them to the feature space and then to the prediction, that specific type of representation is beneficial because it allows the network to separate noise and the information and the data that the images themselves contain. The other thing that is interesting to think about is that certain tasks might be easier or harder from the point of view of the network itself. For example, if you ask a clinician to predict what is the age of a specific brain, or for example, something silly like the sex of the patient, you would need to use skills that they're not used to use on a daily basis. They will need to try to find things that they might not be very useful from a day-to-day point of view of looking at images. So actually clinicians might find it quite hard, for example, to find out what is the gender of the patient from an image itself. However, if you ask them, for example, can you diagnose the patient if that patient has a brain tumor or not, that is something that they're used to do and is something that they can immediately grasp. From the point of view of neural networks, sometimes the opposite happens. Sometimes if you're trying to, for example, predict someone's age from an image, that is something that the model can do quite well, and there's a huge amount of literature trying to do that. And many models can achieve pretty good accuracy of around plus or minus 4 or 5 years of age from an image. But this is a task that is very hard for a human. However, other types of tasks, like for example, being able to predict if a patient has a tumor or not, can actually be quite hard to do because tumors are super complex. They can show up almost anywhere, and the images that are acquired can also have a lot of variability. What I'm trying to say with this is that sometimes there are certain features that can be very trivial when solving one task or another, and depending on the network that we use, those features might be easier to learn for one network or might be harder to learn for another one, and vice versa. That means if you're solving for multiple tasks at the same time, you have a higher chance of your network being able to know how to solve for one of the tasks, and by solving for one of the tasks, the other task can then use the same features, which are likely to be biologically informative, to be able to predict that task. So if you're trying to learn a set of features G, those features G might have a very hard to learn and non-obvious set of features when you're solving for task A. So if you're trying to only learn task A, it's very likely that you will not be able to learn those features G. But those features G might be very obvious from the point of view of the network if you're training for task B. But the interesting thing is when you're training for task B, you can then basically take the same features that you've learned for task B and apply them and use them for task A, and now task A has those features available to it, which means you suddenly have gained this new knowledge that you didn't have before. Obviously, the features they're trying to learn can be quite complex and they can interact with each other. Being able to learn one feature might make it much harder to learn another feature. And it's something that is not something that we prescribe, it's something that is just part of the optimizer that we're using and the loss function that we're optimizing for. But by optimizing for multiple tasks at the same time, what's happening is in order to solve for task B is allowing task A to eavesdrop and to be able to reutilize features that are useful for task B to be able to solve for task A. And that gives it this extra degree of generalizability that you might not have from the outset. So basically, this surrogate task, this secondary task B, which we might or might not be interested about from the beginning, we might just be using it to be able to optimize a better network. That specific task B can just be used as a hinting task so that it supports the optimization of task A. Another way to think about multitask learning is really the concept of representation learning. You're trying to learn a set of feature representations of the input data, which you're then able to use for whatever task you have in mind. And multitask learning forces the network to find representations that other tasks also prefer. That's this idea of tasks having common features. And because you're learning common features between task A and task B, if you now have a new task, let's say task C, the same features are also more likely to be useful for task C. And because they're more likely to be useful for task C, those features are likely to be more biologically informative, and because of that, better at generalization. So really, multitask learning gives the network, when learning the parameters from two tasks at the same time or multiple tasks at the same time, it gives it some degree of inductive bias to find things that are common across tasks, and those things tend to have biologically plausible meanings most of the times. Because of this, it also helps to reduce overfit quite a bit. So far, multitask learning is pretty much a no-brainer, at least given what I've just told you. But this is not necessarily the case, because in certain situations, it might actually not work very well. So neural networks, at least a certain type of neural networks, not necessarily convolutional neural networks, are universal function approximators. So what they do is they map an input to an output space given a family of functions, and they use the parameters to fit that function that maps input X to an output space Y, right? And that fitting process is a fitting process that has a limited number of parameters. If the number of parameters we had was infinite, and if the amount of processing power we had was also infinite, and the amount of data we had was also infinite, then we might not have those issues. But because we have a relatively limited amount of data, and because the amount of parameters we have are not limited, if you're mapping an input X to an output Y, and you're trying to, rather than map it to one single output Y, you're trying to map it to Y1, task 1, and Y2, which is, for example, second task, the network now needs to share its parameters, the number of parameters the network has. They need to be shared between these two tasks at the same time. Which means if you are in a setting where you are very parameter deprived because, for example, you're bound by GPU memory, multitask learning can actually make the performance of certain learning systems worse. And the reason for it is, again, as I was saying, because the network needs to share parameters at the same time. This image here that you're seeing is a network that takes an input image and it tries to solve for multiple things at the same time. It tries to find boundaries of images. It tries to find surface normal, so the orientations of the surface of different objects in the image, the saliency, if they are foreground or background objects, do semantic segmentation, so you might want to segment the horses and the humans. You might want to, for example, localize the heads and the torso and the arms of the humans. So the network's trying to do many things at the same time. And you might argue, okay, the network's trying to do all of this, and it kind of makes sense to ask the network to do all of these at the same time, because if a network knows how to segment, for example, it will likely know where the boundaries of the objects are, because that's necessary for segmentation. Same thing with saliency. I mean, saliency is very highly correlated with semantic segmentation. So it makes sense to train a network on all of these things at the same time. But basically what you see is some of these methods, which is the one that is named here as ours, has the same and often slightly worse performance than the method that is trained on one single target. So for example, if you're only trying to segment and you're using all of the parameters of the network to segment the objects, then the network doesn't need to waste capacity, for example, understanding what surface normals are, which means you can use more parameters from the point of view of segmentation. Obviously, this is maybe a little bit of a strong statement when I'm saying that is not necessarily the best thing to do, and you are restricting yourself to a subset of parameters, because it really depends on the architecture of the network and your learning scheme and everything else. But one thing that you have to take into account, and that's what I'm trying to convey here, is that if you are in a parameter deprived setting, or in a setting where you don't have enough data, where your model is not big enough, it's very likely that your network is going to have a degradation of performance, because it only has access to a restricted amount of parameters to be able to solve for the same problem. And that can cause some problems when it comes to performance. That does not mean that the network will not generalize well, or even better in certain situations, but it's very likely that for individual tasks, a network that has more parameters and sufficient data trained only on one task can often result in better performance than using multiple tasks at the same time. Another thing that happens is when your data sets are very, very large, when you're dealing with large data sets, often multitask learning is not helpful. The reason that is not helpful is because your network needs to actually form very robust representations to be able to achieve high accuracy on training data that is very large. If the training data is really, really, really large, then your network cannot find feature representations that allow it to overfit to that data because you have too much data to overfit. So it needs to learn features that are actually very robust and very generalizable, which is why big data is so important in the medical setting, or actually in the deep learning research world as a whole. And you normally see what these results that you see here on the right of these slides, where multitask learning tends to have slightly worse performance than the model that is trained on only one task. So for example, if you train a VGG to be able to predict the age of a person from a picture, it gives you a mean absolute error of 7.32, while if you use multitask learning, it will end up with a slightly worse result of 7.92. Same thing with, for example, predicting the gender of the person in that picture, where with one task you will have, for example, an accuracy of 0.9, and when you're doing multitask sharing, that accuracy goes from 0.97 to 0.906. So it goes down slightly. And this is very common, and that's because the training set is very large. When the training set becomes much, much smaller, that's where things start getting interesting. So if you're going to apply a fully naive approach where you're just averaging losses from, for example, two different heads, which we're going to see in the next slide, you might end up with the results that you see here, where, for example, your regression for age is 8.7, which again is slightly better than if you're going to do multitask. But for example, if you're trying to predict gender, then the result changes slightly, where multitask now starts having a slightly better performance than a single task. Obviously, in the computer vision setting, data sets tend to be larger. So here, when people talk about small data sets, they're still quite large compared to what we normally have in the medical setting. And also, the input data is often in 2D, and our data that we use in medical imaging is very often in 3D, sometimes 4D, 5D. And because of this, these results actually can be very different between the two domains. In the medical setting, multitask learning can actually be very helpful for very small data sets. When you're training these neural networks, it really depends on the tasks themselves. So the architecture that you use and the architecture that you decide to prescribe, to build in order to be able to solve for multiple tasks would change depending on how much you think the two tasks are very related or unrelated. For example, if what you want is your network to share parameters at the very input of your network, so the first few layers of your network, which are trying to extract very localized features, things that we are normally calling high resolution features or high frequency features. So those high frequency features tend to be extracted in the first few layers of the network. And if we think that task 1 and task 2 only share those features, we might want to, for example, use the architecture on the right, where an image, for example, is fed into a convolutional neural network with one layer or a couple of layers. You're extracting some features which are common, and then the way you compose those features to be able to form objects or, for example, classify different types of pathologies or the gender of a patient, for example, those are things that that will have two completely separate tracks of the network. So they will each one have their own set of parameters, because we're assuming from the outset that the parameters are not shared as soon as we go a couple of layers into the network. On the other side, if the two tasks are very, very related, for example, if you're trying to diagnose two different conditions, but where the patients might have both conditions or neither conditions at the same time. So if you're modeling disease diagnosis as a separate process for each disease, for example, not having dementia versus having dementia, and then not having a stroke versus having a stroke. Those two things obviously can be independent, and they are independent most of the times, but they can also happen at the same time. but those two tasks can have certain similarities in terms of their representation, in terms of the kinds of features we want to extract. And because of this, we might actually want to have a very different architecture where most of the layers of the network can be the same. So we're putting several layers one after the other. They have a lot of similarities. So we're assuming that they're similar from the outset. And we're only splitting the parameters and saying task 1 and task 2 will have different parameters very close to the end of the network. This is basically giving the kind of inductive bias to the network that says most of the representation should be shared, and only at the very end, when you're putting the different features together, and then, for example, doing a fully convolutional operation to some output space before passing it through a softmax, that last step is the only one that will have different parameters for the different tasks. So most multitask learning tends to use this idea of what is called hard parameter sharing. We are literally forcing the network to use the same convolutional kernels, the same fully connected layers. Every single thing is the same between the two tasks up until the point where they branch out. This is what is called hard parameter sharing, because the parameters are shared until they branch out. But there's other ways that you can do multitask learning without forcing the network to have absolutely shared parameters. You can use something which is called soft parameter sharing. So the idea of soft parameter sharing is, let's say you have three completely separate networks here. You have, if I turn on my pointer, actually my laser pointer, which is this one. If you have one network here called network A, which is solving for task A, and network B solving for task B, and network C solving for task C, what you can do is you can put an extra constraint that says the parameters between that layer of the network B and that layer of the network C should be similar. They don't need to be the same, but they need to be similar. And for example, one way of doing this would be to put a prior, like an L2 loss between the parameters. So we're saying these parameters here should be close, but not necessarily the same. And by forcing these parameters to be close to each other, we are communicating information that might be shared. So obviously gradients will flow in this direction, and gradients will also flow in that direction. So the parameters will have information from all of the tasks, but in the end, we'll end up with three networks that have completely different set of parameters. It's just that the parameters will be slightly linked via the amount of constraints that we put and the amount of regularization that we introduced between different layers of the network. An obvious application of multitask learning that many of you probably have seen because it was picked up by the media and because of its maybe not very elegant use was the idea of trying to predict the age, the gender, the hair color, and different other properties, like for example the ethnicity of someone from pictures, which obviously is not necessarily something that we should be doing anyway. But the point here is to what people were trying to show in these papers was that some of the characteristics that are important to predict someone's age and gender and ethnicity and hair color are correlated, or at least they might be important for each other. For example, someone of a certain age and a certain gender might have a different presentation than someone from a different gender would have at the same age. And because of this, it's important that we're modeling and predicting all of the things at the same time, because they often have a very positive interaction. The different features that we're learning for different tasks can interact in a very positive way. Obviously, it has many advantages. It learns this representation that is often more robust, but it also means that we tend to need more data, we tend to need richer labels, and these labels also can have a certain amount of noise in them, which might make the problem very complicated. An obvious example of multitask learning being used in a medical setting is this paper entitled Deep Learning for Multitask Medical Image Segmentation in Multiple Modalities. And the problem that they were trying to solve is that they want to have this segmentation network that can segment different structures from different organs. In this case, they had 6 tissues in the brain. They had the pectoral muscle in breast images, and they also had coronary arteries in cardiac images. And they wanted to basically create a network that had some common features to be able to segment all of the images at the same time. And this obviously makes sense because a lot of the features that are learned on the first few layers of a network are very local features. We're trying to find contrast areas. We're trying to find things that are shaped in certain ways, contours of objects and things like this. So if you're trying to train for 3 different object segmentation networks at the same time, and some of the features are shared, then the network is going to be able to use some of the representations for example, the brain tissues to be able to help segment the pectoral muscle in breast images a little bit better. And I mean, the results that they got in the end was that the segmentations were comparable to the ones that were trained on single networks, which is a little bit of a negative outcome in the end. But it did show that the network was able to learn multiple tasks at the same time. And the other thing is, and that's something that is really interesting, is that but the authors did not explore that part, at least not to the degree that they probably should have, would be to take those networks that have been trained on 3 tasks and show that the same features that were common for those 3 tasks might also be applicable to a 4th or 5th task. Because that means the network now has learned features which are useful for many different tasks and not only those 3. So just as a very quick figure, this is a figure from that paper, and what you can see is that during their own training experiments, they are cycling depending on the input image that they're giving the network. So sometimes they give the brain image, which will have the 6 labels. Sometimes they give the breast MR, which will only have the pectoral muscle, and sometimes they give the cardiac CTA, which obviously will only have the coronary artery, and they're cycling between them. Often overlapping tasks and sometimes not overlapping tasks, to be able to force the network to see different tasks at the same time, and also gradients that come from different locations. So sometimes gradients might only come from one task, sometimes gradients might come from multiple tasks at the same time. And here there's another image from the same paper where authors are showing the 3 body parts, in this case the brain, the breasts, and the heart. And what you have after that is the ground truth, a network trained with 1 task, and 2 networks trained with 2 different tasks, and network trained with the 3 tasks. And what you see, and I mean, the differences are actually relatively small, but you do see them. For example, when you look at the CTA image of the heart at the very bottom, you see that when you're training with all of the tasks at the same time, some of the coronaries that you see at the very bottom show up in the right number compared to the ground truth, but they do not show up in the right number, for example, when using 2 tasks or often using only 1 task. So those small details can actually make a big difference when using this in real-world applications. Okay, good. Thank you very much for listening so far. So what I would suggest now is that you pause this video and you load up the Jupyter notebooks and you go through the practical session, part 0 and part 1. Obviously, during the practical session that we'll have this week, you're going to be doing the same exact exercises, and I'll be going through the code and the solutions of the code. But it would be really helpful if you could take some time, go through the practical session 0 and 1, because I hope that by going through that section, you'll learn a little bit more about what multitask learning is, how it actually works, which will help moving forward to the rest of the lecture. Okay. So now you've looked into multitask learning and how do you optimize for 2 tasks at the same time. One of the issues that normally plagues multitask learning is the fact that different tasks often have very different loss functions. For example, if you're looking at this example that I was giving before, of trying to regress, for example, the age of a patient from an image, and at the same time trying to diagnose those. Regressing age will be something that will be done via regression loss, like an L2 norm, and the classification of the patient, the diagnosis of the patient, will be done via something like a cross entropy loss. And those 2 losses have very different scales, right? What I mean by scales is that the numerical value of the losses will be very different. If you're, for example, looking at an L2 loss, it's going to be scaled depending on the root mean squared error of the difference between the prediction and the truth. So let's say if you're looking at age, the age of a patient will vary between let's say, if you're only looking at adult population, between 20 and 80 years of age. That means any mistake you make is going to be a number that is going to be your prediction minus the true age, which is going to be a value between 20 and 80, which means your error is going to be maybe around 5, 6, 10 years of age. And that error is then going to be squared via the L2 norm and is going to give a value which might be in the low hundreds, for example. This is quite a large value to have in terms of numerical value for a loss. If at the same time you're trying to diagnose a patient, the cross-entropy value itself is going to be much, much lower than hundreds, unless obviously your problem is extremely complicated. It's theoretically possible. But in most settings, cross-entropy is going to be in the 1 digit, maybe even lower than that type of numerical value. So the scale of those two losses is very different. So the first thing that most people will think about is to do what is called loss weighting. But there's other methods like grad norm, which we're going to see later on, that will help you mitigate those issues. Let's say now that you're trying to train a network to perform both an image segmentation and an image classification at the same time. For example, segmenting a brain tumor and classifying if the patient does have a brain tumor or not. Your loss function might look somewhat like, for example, the one that is written here, where you're trying to optimize for cross-entropy for the segmentation, cross-entropy for the classification problem, and then a regularization term, for example, weight decay. If you're trying to do this, the order of magnitude of the cross-entropy for segmentation or cross-entropy for classification might be very different. So they might just have different numerical values. One of them might be around 2 or 3, for example. The other one might be around 1 or 0.5. And that might look small, but it does mean that every single time you make an update on the system, the gradients coming from one of the losses will be 2 or 3 times or 4 times bigger than the gradients coming from another one of the losses. That means that the network is going to optimize more for the task that has the higher numerical value, as long as the gradients are stable, obviously. And it's going to follow that gradient more because it has more impact on the final numerical value of the total loss, so the value of L here. The way to mitigate this, obviously, is by reducing the influence of the loss that has the higher numerical value, so that after multiplying by a small value, let's say 0.2, you're going to make that value 5 times smaller, and by making the cross-entropy segmentation, for example, 5 times smaller, it might then end up with the same, roughly the same numerical value as the cross-entropy used for classification purposes. Okay, let's then go back again to the Jupyter notebook, and let's go through part 2, which is doing the same thing as you did before, but changing only the weights of the loss functions. And you'll see the effect that that will have. It's a very simple experiment, and it's just a very small change to the code, but hopefully we'll see and we'll show you of the effects of rebalancing the weights of the different losses for the point of view of the task that we were solving. Okay, back to the lecture. So if you're trying to do explicit loss function weighting, so changing the weight of a loss function explicitly from the very beginning, it does have certain limitations. First part is, obviously, this is quite a hard process to do. You need to know which task will be dominant, and you need to be able to know if that dominant shifts during the training itself. What I mean by that is, if you initialize the training of a network, it might be that one loss function might be, for example, 1 order of magnitude larger than another one. So you say, okay, I need to divide my first loss function by 10 to change that. You do divide it by 10 in your code, you start the training again. They now look like they are in the same scale, but maybe a few iterations down the line, one of those loss functions would have reduced enough but the other one maybe has not reduced sufficiently. And because of this, they might now be an order of magnitude different again in their numerical value. What should you do? Should you stop the training at that point, change the weights again manually, and continue training the network further so that you re-harmonize those weights together? Maybe that's not the best thing to do, right? You probably have something a little bit more elegant that you could do to try to make sure that as the network is training, that the losses are roughly of the same order of magnitude during the full training process. And obviously, this problem is much, much worse when you have many different tasks at the same time. If you have 3 or 4 tasks at the same time, and on top of that you have regularization terms, those can interact in a very odd way, and they might fluctuate a lot. The other problem that you have is that obviously you cannot change the numerical value or the weights at every single iteration or for every single batch, because there is stochasticity in the process. So it might be that for one specific batch, task A had a very low loss and task B did not, but it might be for the next batch that things are very different. That means you cannot be as trivial as just changing it every single iteration. Otherwise, you're going to be susceptible to these variations that happen between batches. Because the numerical value of the loss function itself cannot be trusted, what you can do is to use the gradient of that loss function instead. This is what gradient normalization is trying to do. So grad norm basically comes in a situation where there is one dominant task that greatly influences the training of that network. And because of that, when you're back propagating through the network, that is where most of the gradient numerical value is coming from, because that's the one that has the highest loss. And the opposite is true for the weaker task, obviously. So if a task is very weak, then the gradient is going to be very small comparatively. So rather than balancing the actual numerical value of the loss itself, what you can do is to actually look at the gradients and make sure that the scale or the norm of the gradients is the same between all of the tasks. So you want all the tasks to contribute the same degree from the point of view of the optimization. So you want the gradient to be of the same scale. And again, why don't you want the numerical value itself to be the same but you want the gradient? Is because obviously, just because the numerical value is of the same size, it doesn't mean that the gradient will be proportional to that, right? The gradient of a function could be anything depending on the function. So it's much better to do it on the gradient itself, because at least you know that the gradient you're receiving from the loss function that you're optimizing for is of the same scale for multiple tasks. And you can do this at every iteration, you can do this at every epoch, and you can also have regularization terms to, for example, minimize a little bit the fluctuations that you might have between different parts of the network or different loss functions while you're training. So a picture that you normally see when looking into gradient normalization is the one you're seeing here. So the image on the left shows what was the approach that we were doing before, where we are simply changing the weights of the different loss functions in the numerical value of the loss function itself. And the interesting thing is, obviously, when you're back propagating through a series of filters, the gradients that you're getting will be unbalanced even if you balance the loss functions themselves. While if you're doing it on the gradients themselves, if you're collecting gradients at the different levels of the network or at the end of the network and making sure that the norms of those gradients are the same, and those norms are the ones that are defining the weights of the loss functions, then you're using the norm of the gradient as the piece of information that is telling you what the weights of the loss function should be, because those are the weights are going to change the scale of the gradients in a way that they then end up with the same norm. One thing that I like to do when teaching any topic in the medical setting is to show that many of these papers coming from the computer vision domain or simple machine learning domain can and do have applications in the medical setting. So I normally tend to present papers that come after different concepts that show that concept being used in the medical setting. This is the example that I'm using here for grad norm, a paper entitled Multitask Localization and Segmentation for X-ray Guided Planning in Knee Surgery. And what they do is they have a framework that tries to perform different things at the same time. They try to localize landmarks, they try to predict a certain region of interest, and also they try to segment the image all at the same time. And they use grad norm as a way to be able to manage all of these different tasks that they're optimizing. This is an image from that paper, and it shows that different tasks have different weights calculated by the grad norm method at different stages of the training process. So if you're in epoch 1 or epoch 200, you're going to have very different weights as the model is training, because the gradients, the norm of the gradients, is changing as you are training. The other part that is really interesting is that this actually tells you quite a bit about the dynamics. Obviously, when a specific objective is optimized, an objective, for example, being able to do segmentation, might be optimized faster than, for example, the task of finding a specific region of interest. If it is optimized faster, then the loss function is going to go down quicker. And because the loss function is going to go down quicker, the gradients after the loss function plateaus, because you already optimized what you had to optimize, then the gradients might become very small because there's very little to optimize. That means that you might want to boost up those gradients so that you continue learning the segmentation task, because otherwise it will just saturate the network. But the opposite can also happen. For example, you might have a task that was very hard at the beginning, but because you're learning multiple things at the same time, maybe there was suddenly a feature that helped that network optimize, and maybe only later on you start getting a lot of gradients back so that you need to scale it down to compensate for it. So these dynamics can be quite interesting and can be quite powerful. So with this in mind, my hope is that you will now go back to your Jupyter notebook and move into the grad norm implementation. Again, it continues the same as the previous experiment, but rather than the weights being prescribed by you, they will be calculated via the grad norm method, and you're going to change the loss functions dynamically during training, and you're going to see the effect that that will have on the training systems. When we're talking about multiple tasks, normally we think about two tasks as both having the main objective. So you want to do two things at the same time, and you want to do two things well. But actually, another concept exists, which is nothing more than multitasks, but where one of the tasks might be less important. This is something that we normally call auxiliary tasks. So auxiliary tasks are situations where you're basically concerned about helping the main task and not actually solving for that auxiliary task. So the auxiliary task is only there to help guide and help the main task converge. And this auxiliary task can have quite a big impact in terms of the performance of the main task, primarily in situations where the learning process for the main task might be very noisy. And the use of auxiliary tasks can help reduce the noise and make the network focus on specific types of features, or extracting certain types of features that will promote certain behaviors from the point of view of the network. Auxiliary losses can also be used in a very different way than multitask losses. For example, if you have a very, very deep network, very deep networks are often useful because they have more parameters, they can compose features in a more complex way, and because of this, they often tend to result in better performance if you have enough data, of course. But they also have other issues. For example, you have issues that gradients might not propagate well through the network, and the network might get stuck and not really optimize very well, which is why you have networks like ResNets that try to really bypass that issue. But another way to do this is to use what is called deep supervision. So the idea of deep supervision is that you introduce a loss somewhere in the network, and that loss might be doing the exact same thing as the main loss. Let's say you want to classify if someone has a disease or not from an input image. The network has many layers, and the ultimate goal is on the very last layer that you're optimizing for diagnosis using a main loss. But this might be actually a very complicated process, as I was saying, because of this vanishing gradient issue. If you were to apply an auxiliary loss somewhere in the middle of that cascade of layers, then the gradients that you would get back would be stronger, because then the gradients are being fed directly into the middle of the network. So you're actually solving for the same task, but you're putting losses in different parts of the network, and those losses make sure that subparts of the network, for example in this image here, the first two layers, will receive a gradient directly from the auxiliary loss, and the remaining third and fourth layers will only receive gradients from the main loss. So the first two will receive both gradients, and the last two layers of that network will only receive gradients from the main loss. And the auxiliary loss here is really there just to try to help, just to make sure that the gradients are flowing and that the network can be optimized. So when you're looking to auxiliary tasks are there to help the main tasks, so they don't necessarily need to be useful, but they still need to be something that the network can do. Otherwise, they will only introduce noise from the point of view of the training process. And it's not because a task is easy that is necessarily useful, and it's not because the task is hard that is necessarily unuseful. So a task can be either useful or unuseful depending on how much it shares with the main task that you have and how much is stabilizing the system itself. I know these words might sound very vague, and they are, because it's a very empirical question as to which tasks might help different types of problems. But you need to think about it as that task is there to stabilize the gradients of the main function and of the main task, and that's its role. You need to find a task that somehow is going to share information and force the network into a feature representation which is useful for the main task. Interestingly, the gradient between different tasks, for example, if you have a main task and auxiliary task, the gradients inside of the network coming from one task or another and the angles that they form actually tell you something about how complementary they are. So if the auxiliary task is helping the main task go in the right direction, then they should be pointing, both of them, they should be pointing roughly in the same direction, and the cosine between them should, for example, be above 0. that means they're pointing roughly in the same direction. If they are 1, obviously they're pointing in exactly the same direction. So if cosine between the two gradients is above 0, it means that they are promoting each other. And if the cosine between them is smaller than 0, it means that they're actually pulling apart. You can then use this information as a way to modulate and change how your network learns. So here's a way of using cosines as part of your learning process. For example, with something called unweighted cosine loss, what you can do is to say if your auxiliary loss and your primary loss have a cosine that is above 0, you want to, for example, use the gradient from your auxiliary loss to optimize your network. While if the angle between them is below 0, then you want to not optimize your network at all. You can also use other things, like for example, you can use the maximum between the 0 and the cosine multiplied by the auxiliary, or you can also project. That means you're taking one of the gradients and projecting it to the other gradient, which is going to change the norm of that and give a step size which is proportional to that projection. All of these different methodologies, basically what they do is that they step in the direction faster if the two gradients agree with each other and if they point roughly in the same direction, and they stop progressing, or actually they either they completely stop or they slow down the step of the optimization if the two gradients disagree with each other. And this is a way for you to increase the robustness of the gradients and to end up in a minima, which is useful for both tasks. So this image here is just showing you exactly what I was saying when I was talking about projections. In this situation, you see that the gradient coming from the auxiliary loss is pointing that way. The gradient from the primary is pointing that way. So what we do is you project the gradient from auxiliary into the primary, you get the vector, and that vector is then rotated back into the auxiliary direction. That means you're going to step in this direction because, first of all, they agree, their cosine is above 0, and you are going to scale it down depending on how much they agree with each other. This is a technique that is not yet very much used in the medical domain, but for example, it is used in situations where we're using language in the medical setting, obviously, because the gradients there tend to be a little bit noisier than they are, for example, if you're trying to segment an image. And this specific paper was using cosine similarities and showing that depending on the different methods that you can use, you can improve the performance of the system by making sure that different auxiliary tasks can help the main task, which was to be able to do the sentiment analysis and the subjectivity analysis of the words that were written in that text. Here are a couple of images from the paper showing that, for example, weighted cosines and projections of cosines, in this case the blue and the red lines, are pretty much the best, both in terms of the primary loss at training time, but also the validation loss at test time. You see that the performance is actually also very different between them, primarily the PW methodology that has a validation loss which is substantially below the other ones. Okay, so with this in mind, please again take a break, look again into your Jupyter notebook, and let's try to implement cosine similarity between a task and an auxiliary, so that you see, first of all, how do you calculate the gradient, the cosine between the two gradients, and how you then use those as a way to weight the step size of the different parts of the network. Okay, so now that you've seen how the cosine similarity works, we're going to look into a couple of other extensions of other ways that you can also make multitask work by using slightly different approaches. One way is to use uncertainty. Uncertainty is something that we're going to learn later in this course, but you can think about it as a way for the network to be able to convey how much it thinks it knows how to make that prediction. So every time it makes prediction, it attaches to that prediction a confidence value, which could be seen either as an error bar or just a confidence score of how much it thinks it knows that prediction is correct. If you're now doing multiple tasks at the same time, one of the things that you might want to do is for the predictions to reach a state where they all have the same confidence, right? Where they all have the same degree of knowledge. So every time you make a prediction, you would hope that the confidence of the 2 or 3 things that you want to do have the same degree of uncertainty. So you can use the uncertainty value itself as a way to balance the different tasks and to be able to then make predictions which are slightly more appropriate. Another thing that you can do is to think about the architecture itself. So we were talking about situations where you might want to split a main trunk very early on if you only want to use the first couple of features as hard shared, or you might want to split it much later on if you want most of the features to be shared except the last couple of layers of a network, for example. The other thing that you can do is to evolve an architecture. So you can start with a network that assumes that all of the layers are shared except the very last. And then depending on a few constraints, you can basically change the architecture dynamically by allowing certain parts of the network to be split across multiple tasks. This process here is a greedy process. So it's a process that will slowly split certain parts of the network in two, and those parts that are split will then become task specific. And continuously, if you keep doing this using a greedy algorithm, you can converge into an architecture that has a representation that is hierarchical, where different parts of the network will be used for a subset of the tasks, but not all tasks. And this is all obtained during the learning process itself. Similarly to what we saw before, when we were looking into soft parameter sharing and hard parameter sharing, there's other types of networks called deep relationship networks. That what they do is certain parts of the network, for example, the convolutional components might be hard shared. And then when the network bifurcates into two subparts, each part responsible for one task, you can basically introduce a prior between them, which acts a little bit like what the soft parameter sharing does, that gives some structure and allows still some sharing of information across multiple tasks, but allows the parameters to become task specific. The other part that is really interesting is the concept of learning when to share. So when we're looking into soft parameter sharing, what you have is you have two networks, and those two networks are connected to each other via this L2 loss. And this L2 loss means that because the parameters need to be somewhat close to each other in order to minimize that loss, that there is a gradient flowing from one network to another, and those two networks are going to end up in parameter spaces that are relatively similar, but still optimal for each one of the tasks. This idea here, presented in this paper called multi-stitch or cross-stitch, is the method that selectively decides when and when not to share information. So if you have these connections, these L2 connections, they can be replaced with mini networks, and these mini networks basically are deciding when one specific layer of one task can share information with another task and vice versa. And those stitches, that connectivity, is learned. So it's something that is slowly evolving and is being adapted to the problem at hand. So certain problems might require more stitching, while other problems might require less. Another approach that you could use, which is similar to this cross-stitch, is something called stochastic filter groups. If you imagine that you have a network that has a certain number of parameters per layer, another way that you can think about splitting the network into two or allocating certain parameters to certain networks is to be able to, at each one of the layers of a network, to decide which parameters belong to task 1 and which parameters belong to task 2. On the top left, you have a figure, which was on the paper, that explains exactly how do you go from the figure on the very left, which is the one that shows that the network starts from a shared component in green, and then after a few layers, you basically split the parameters in two sets, a subset of parameters looking to task 1 and another subset of parameters looking to task 2. And what this paper proposes is to be able to learn the percentage or probability that at each one of the layers, the parameters are going to end up in task 1, task 2, or task shared, while task shared is obviously the component that is used by both tasks. And if you think about it, what you're learning is really this vector of three values, each one of them between 0 and 1 and adding up to 1, that dedicates a certain amount of parameters to those specific tasks. And you can do this by using these stochastic filter groups, which is basically a specific type of operator that maps a certain set of parameters to a subgroup, to one of these tasks, task 1, task 2, and shared, according to a value of p. And this value of p for each one of these p1, p2, and ps are being optimized during training and are also sampled at each forward pass. That gives you two things. First of all, it gives you a parameter allocation that can be optimized for each one of the tasks, which means every time you train the network is deciding how many parameters do you need for each task and how many parameters should be shared. But also because every time you do a forward pass, you're sampling from this distribution, you're getting slightly different realizations every single time you do a forward pass, which actually gives you a really interesting insight towards how uncertain the network is in terms of the prediction that it's making according to a variety of different architectures. If you apply this methodology in a medical imaging setting, what you'll end up is with something like this, which is exactly what you'd expect in terms of parameter allocations. So the network learns that, for example, on the first few layers, it should not allocate any parameters to task 1 or task 2, and everything should be in the shared task. And you see that the features that the network learns are very global. They describe, for example, the fatty tissue or the soft tissue of these patients or the bony areas. A few layers in, what you start seeing is that some parameters start getting allocated to the segmentation task, some parameters start getting allocated to the synthesis task, and some parameters remain as shared. Later on, in the very last layer, you see that the parameters are now either allocated specifically to segmentation or specifically to synthesis, and no parameters are allocated to shared parameters. And after that, obviously, you pass the segmentation layer into the softmax, and you end up with the segmentation, the same thing through a regression layer to get the synthesis. But what's interesting here is if you look at the content of the, for example, on the second last layer, the segmentation part of the second last layer in blue shows you primarily the regions that are being segmented. The synthesis part in red at the bottom of the second layer shows you regions that are very important from synthesis purposes, for example, things like bone or the fatty tissue, which are going to influence your final CT that you're trying to predict. And the shared component, again, gives you kind of mixed information. It's a little bit hard to interpret here, but it is still information that is useful from the point of view of being able to segment and synthesize these CTs. Okay, so far we were discussing aspects around multitask learning. So really this idea of you having multiple outputs to the network and trying to balance the different loss functions according to a few different approaches. And if you think about it, we were using these other surrogate tasks to be able to optimize the network and guide the network learning into the direction that we want to. But in certain situations, that kind of information is actually available at training time. So for example, when we were saying that being able to know someone's age might be useful to be able to, for example, understand if someone is a male or a female, or if someone, for example, is part of a specific ethnicity. All of those things are true. But rather than starting from an input image and giving, for example, the network, the sex and the age of a patient as variables that the model needs to predict, what if we were to give one of those variables as input? Would the network then be able to create a representation that is that is specific to the task that we actually want to solve? For example, if we were to give a network, let's say the age of a patient, a picture, and the age of the person in that picture, would it be easier for the network to then figure out if, for example, that patient is a male or a female? That's something that would be really interesting to understand. And this is something that is actually very common. If you think about it in a healthcare setting, these variables are available to us. It's something that we could use. It's something that is available in the clinical healthcare record. So should we be making use of that kind of information as an input, or should we be making use of that kind of information as something that we would like to predict? For example, here, if you want to predict if someone has a normal or a abnormal brain, you might want to use multiple input images, but you might also want to feed other types of information, such as patient demographics, or, for example, a blood sample that they got collected when they were admitted into the hospital. All of these things are something that will be really interesting to explore. And obviously this idea has applications much beyond surrogate information that might be part of different components of the clinical healthcare system. Many times the images themselves have information beyond the pixels. For example, the DICOM header of a medical image will contain characteristics of what was acquired and how was it acquired. And currently that information is being used. For example, if we were to take the parameters of an acquisition, for example, the physics parameters of an MR acquisition, and feed those into the network, the network will then know more than just the pixels that it's observing. So you can use the physics parameters as a way to disentangle certain effects and be able to do measurements that are much more appropriate. Here's an example on the left of the same patient being scanned one day apart on 2 different scanners. And you see that by changing the physics of acquisition, the images look very, very, very different. And that's because different MR machines might not be able to acquire exactly the same image in exactly the same way, even after calibration, just because they work differently. So if you can feed the physics parameters into the network can then understand that the content of the pixels doesn't say everything. And by using these physics that he has learned, or by making use of these physics to make the predictions, he can then, for example, be able to segment the anatomical regions, in this case the white, gray, and CSF, much better than you could do before, purely because you have access to these physics quantities that tell you that, for example, the white matter, gray matter contrast will be different in this image compared to this other image. And you can then estimate volumes that are much better than before. Excellent. So last part of the practical Jupyter Notebook. What we're going to do now is not really multitask learning, is purely exploring the idea of adding more information into the network and trying to understand if the network can do something differently or something better. For example, if you tell a network not only a picture of someone's face, but also the age of that person that is in that picture, would it then become better at distinguishing between, for example, male and female faces? That's something interesting because it then will tell you that the network has more capacity to be able to disentangle the sex or the gender of someone by using this surrogate information. Okay, so as a summary of today's lecture, first of all, we learned that networks can solve for multiple tasks at the same time. So a network can make multiple predictions, and you can train the network appropriately by balancing how the different losses of these predictions should weight the learning process itself. Multitask learning does not always make the performance of a system better. For example, if you are in a data-heavy regime, it might be that the single-task network has more parameters and sufficient data, and because of that will work better than trying to solve for 2 things at the same time. But in situations where you are in a data-deprived setting, or when the training signal is very unstable because of the presence of noise or the labels not being very good, or when generalizability is not great on the trained model and another surrogate task can then be shown to improve that generalizability, those are the situations where multitask learning can become really, really important. The way you balance the different losses, or the way you balance the different tasks, can be done either in the domain of the loss itself by, for example, changing the magnitude by multiplying by a weighting factor, or it can also be done in the domain of the weights themselves and the gradients that you estimate from those weights, so that those will be the class of methods that we've seen, such as gradient normalization. There's also other classes of approaches, such as the cosine similarity, that allow you to describe the consistency between multiple tasks, and depending on that consistency or lack of thereof, it will then be able to improve the way that you train and the stability of that training. And the last thing we saw was that if you leave the multitask setting and you start looking to multiple input type data, multiple inputs can make some of the systems better by providing information that might be useful for the prediction to be made that was not necessarily present on the input image. So I hope you enjoyed this lecture, and I really do hope that by the end of this lecture you now know what multitask networks are, you understand how to balance and influence the different types of tasks that you might have prescribed your network to do. You understand that auxiliary tasks can help regularize the learning process itself via things like cosine similarity, and that often by providing more input information to your network can also help the regularization and achieving much better performance. And with this, I will also open up for questions during the practical session itself. So please take some time, go through the Jupyter Notebook, do your best. We will go through the Jupyter Notebook together during the practical sessions. And if you have any questions, I'll spare 10 minutes at the end of that day for us to go through those questions. Thank you very much.